Well, hello everyone. I'm Nuria Fernández, and I am happy to share my findings on the degradation of conventional and biodegradable microplastics in the marine environment. I've worked in the University of Algarve with my supervisors, Dr. Isabel Marin and Professor Maria Clara Acosta. So, to introduce the topic, I would like to briefly explain why it's important to study plastic pollution. And this is because plastics are lightweight, cheap, and durable, and these properties make them a suitable and perfect market product. In this graph, we can see that the manufacturing of plastics has experienced an exponential increase, basically since the 1980s. Reaching values of over 400 million tons of plastic production only in 2019. This massive production is having a drastic impact in the marine environment, to the point in which up to 5 to 13 million tons of plastics are entering the marine environment every year. Also, the COVID pandemic has supposed an increase in the search of plastic use, mostly in the single-use plastic products, and this is leading to an increase of waste entering the marine environment as well. For all of these reasons, plastics are nowadays considered as one of the main pollutants in the aquatic environment. On the other hand, it is also important to know what microplastics are and why to study them. Well, microplastics are small plastic particles of less than 5 millimeters in size, and they can easily absorb the chemicals from the environment and also find bacteria attached to them, even with the formation of bacterial biofilms. This is posing a risk to both protected and species relevance to human consumption, since they are, because of their small size, they can easily enter the aquatic food chain and be transported from the lowest trophic level, such as phytoplankton, and be transported along the entire food chain, reaching the human body. Okay, our two main polymers of study are the low-density polyethylene and polyethylene terephthalate, and because they are two of the most used polymers worldwide, our aim here is to assess the potential marine bacterial communities have to biodegrade them. This way, we can also help finding cheap and environmentally safe solutions to alleviate this problem of plastic pollution, and as well to broaden the study of the biodegradability of these polymers in the environment. In this study, we formulated two main hypotheses. First, we were expecting a small biodegradation of both polymers, since our experimental time was shorter than in similar studies. And second, we were expecting a higher biodegradation of the biodegradable polyethylene terephthalate microplastic particles, since they are labeled as biodegradable. But where do our samples come from? Well, they come from two marine caves in Sagres, in the southwestern Portugal, which are the Cathedral Cave and the Cage Suiza caves, such as Julius, and where professional divers collected a total of 36 samples. But among these 36 samples, only 6 of them, 3 from each cave, were selected for the screening. All these samples come from different marine organisms, as we can see in the table, but only the inoculum number 18, coming from the species Didenium sp within the phylum Tunicata, was selected for our biodegradation experiment. As I've been previously mentioning, our two polymers of the study were the low-density polyethylene and the biodegradable polyethylene terephthalate. They both come from commercially available plastic bags, from which pieces of 2 times 1 millimeter were cut. Here we can see the molecular structure of both polymers, which is really important for this study, as polymer degradation depends on the number of carbons present in the molecule and the structural arrangement of it. Low-density polyethylene and polyethylene terephthalate are two of the most used polymers worldwide, and we can find them in plastic bags or garbage bags or bread bags, such in the case of polyethylene, low-density polyethylene, and here the polyethylene terephthalate can be found in plastic bottles, and in the case of the biodegradable one, which is where our samples come from, they are also now commercializing biodegradable PET. Okay, so previous to our biodegradation experiment, we performed a screening. Why did we do this? Because we had, since we didn't have the time to carry the experiment for the 6 marine bacterial communities recovered, we had to select the one with the greatest potential to degrade both polymers, and this is why we did this test. But what did we obtain? Well, we didn't see statistical differences among the 6 bacterial communities, but visually we could see that the highest potential and the main differences were obtained in the ones in the samples recovered from the Cathedral Cave, which are the inocula number 4, 18, and 21. And among these 3, the inoculum 18 showed the most promising results and was therefore selected for the biodegradation experiment. Okay, moving into the biodegradation experiment, it consisted of 5 treatments with 2 controls. The negative control with the microplastic particles and without the inoculum, and the positive control with the inoculum but without the plastic particles. And the other 2 treatments with both the polymer and the inoculum. We used 3 replicates, 4 sampling times after a week, after 2 weeks, after a month, and after 45 days, with a total of 65 samples and with a concentration of 1 microplastic per milliliter. Different variables were analyzed at all sampling times. So during the whole experiment, we measured the optical density to monitor the bacterial growth, as we were expecting a higher bacterial growth in the samples with inocula compared to the controls. We also measured the pH variations and the changes in the functional groups through FTIR. FTIR is a widely used tool for polymer degradation, as it allows for the straight identification of absorption bands at given position that can be modified as polymers degrade. This way, each glass flask at each sampling time and treatment was filtered to obtain the plastic particles, and 3 of these plastic particles were analyzed through FTIR to obtain the respective spectrum and analyze it and compare it among time and treatment. Also, at the end of the experiment, we measured two other variables: the chemical oxygen demand, which indicates the amount of oxygen that is necessary to oxidize the particle, the microplastic particle. So the lower the value, the more biodegraded the particle will be, and vice versa. Also, we analyzed through scanning electron microscopy the changes in the plastic surface of each polymer. Moving on to results, we must say the first variable measured was optical density, where we obtained what we were expecting, so a higher bacterial growth in samples with inoculum. And for both polymers, we obtained statistical differences. For the pH, similar results were obtained, in which higher pH was observed in the samples with inocula, and only a statistical significance was obtained in low-density polyethylene. This is important because it's indicative that bacteria require certain alkalinity in the medium to act and to biodegrade the plastic. Moving on to the FTIR, we must say that we compared the spectrum at initial time, so before the experiment, and after the 45 days of incubation time, which is marked as T4. For both polymers, comparing the controls marked as K, and with the inocula as marked as I18. So in this case, for the low-density polyethylene and the controls, the spectrum does not change throughout time. However, when we move into the samples with the inocula, some changes are appreciated. First, we have to say that there was a decrease in the main peaks of low-density polyethylene, which are these 2, which were significantly significant. Also, we saw, this decrease is indicative of polymer degradation, according to Regendes and colleagues. Also, we have observed the appearance of this peak at 1,648, which is due to aldehydes and the formation of aldehydes and ketones, and also the appearance at this peak at 871, which leads to the formation, is attributed to the formation of nitric ion. All of these changes and shifts are indicative signs of biodegradation. Well, in the case of biodegradable PET, in the case of the controls, we don't see a lot of differences in the spectrum, just the appearance of this peak at 3,700, which is attributed to a nitrogen-hydrogen stretching. In the case of biodegradable PET with inocula, the main changes occur in the footprint region, and also we also observe the appearance of this peak at 1,600, which is, as mentioned earlier, attributed to the formation of aldehydes and ketones. And we also observe an increase and a decrease in some peaks, such as in 1,400 and 1,020, and the appearance of this peak at 874, which are attributed to the formation of aromatic compounds. They are all statistically significant. These shifts could indicate that the polymer is being degraded. However, there is lack of information regarding the changes in the functional groups of this polymer. But these results could, in this way, in this sense, pave the way for further interpretation of the biodegradation of polyethylene and terephthalate. In the case of the results of the chemical oxygen demand, as we were expecting, we obtained higher values in the controls compared to the ones with inocula, and this is indicating that that these particles with inocula are more degraded, so they need less oxygen to be degraded. This is a biodegradation sign. In the case of the scanning electron microscopy results, again, we compared, we analyzed both particles with both polymers, and we compared the controls with the ones with inocula. The surface of the particles in the control show that are much smoother, and there is no signs of bacteria attached to them. Whereas in the case of the ones with inocula, we observe some fractures and holes in the surface, and also some bacteria added, and the formation of bacterial biofilms. These are all indicative of polymer degradation. In the case of biodegradable PET, similar results are obtained, in which the controls surface particles, they show smaller surfaces with no bacteria, whereas here in the ones with inocula, we can see all the bacteria attached with holes, and here is a clear example of a bacterial biofilm, and these are all indicative of polymer degradation. So to conclude, we must say that both polymers exhibited signs of biodegradation because we saw some changes in the chemical structure of the microplastic of both polymers. We saw an increase in the bacterial growth and in the pH as well, a decrease in the chemical oxygen demand, more specifically in the low-density polyethylene particles. This does not meet with our previous hypothesis, in which we're expecting the contrary, and this could indicate that maybe what is labeled as biodegradable in the end is not that biodegradable. And we also saw modifications in the surface feature of both plastic polymers. Therefore, the selected microbial community has potential to biodegrade both polymers. However, these are only early signs of biodegradation, so a longer incubation period may have shown clearer biodegradation signs. Thank you very much for your attention, and yeah, I would like to thank the ProBioma project for the financiation of this whole project. Thank you very much. If you have any questions, don't hesitate to ask.